All right, guys. Um, Hopefully, I got plenty of time here. It's not showing me how much time I have left on my phone, but hopefully, I got lots of memory. Welcome to Friday. I guess this is the last of our daily meetings, which is fine. Shouldn't affect us too much. I guess we're gonna do like the first half the first day, if I read that email correct. The second half the second day. Look over the email that was sent out. I think by Mr. Slaughter, possibly by Mrs. Snyder. But look over that information. Obviously, it's going to be important, and act accordingly. I'll probably post everything. I might post everything like the first day, but you can just like you can now. Honestly, for me, you have lots of time. I don't have a set class period where you need to come in and listen during that time. This is all YouTube video stuff, so it's there. It's available to you. You can actually come back and look at it later. But again, one of the things that I want to remind you of is one of the ways that I try to make sure that you guys watch it that day is by putting a little question in there. I'm going to do that again today, so I'll add a little question to this lecture, probably sometime soon during the lecture. It'll be embedded into it, and I'll ask you guys to put that into Google Classroom. I put all of my lectures now in as an assignment, so all you have to do is when you go to find the lecture, you will also find on the right hand side of your screen an area to upload the paper or whatever it might be to that assignment. So you can write the answer to my question on a separate sheet of paper and you can upload it, or you can just put it on a Google document. Whatever works for you. Whatever I know, and again, I know some people are having trouble with Google Classroom. I even had some trouble with it the other day. Sometimes there are some glitches. My question for you is just like I asked in the having trouble with Google Classroom video, what are you doing to resolve the issue? Because if you're just trying to upload it the same way over and over, that's not going to resolve the issue. Okay, you got to do something different. You got to try something different. Try to upload it via your phone. Again, try to put it on a Google document. Try to decrease the quality of the photo. If it's just a question, okay, it's not hard. I don't have to be able to see it in 4K. Okay, I can still probably view the answer to that one question in probably 720p. Okay, so you can shrink that size down and make it easier to upload for Google Classroom. And listen, guys, I know too that there's a lot of people using Google Classroom that weren't before. I know in our class we've always used it, at least to some degree, but there's a ton of people using it now. So they have to make amends kind of for that huge influx in users onto that platform. So, unfortunately, because I was there first, they shouldn't be able to do it, but whatever. All right. Today, guys, we are going to continue on talking about momentum. It's not going to be a long video. I mean, I'm thinking like maybe 20 minutes, maybe less, depending on how much I chatter. Um, but let's go ahead and pray before we get started, and we'll talk a little bit more about momentum. Bow with me as we go to the Lord. Lord God, I just want to thank you for today. Thank you, Lord, for the opportunity that we have to be here on this beautiful Friday. Lord, help us to enjoy the time. Maybe even I was out yesterday mowing for the first time in a really long time, Lord, and that was nice. It was really enjoyable. And I just pray, Lord, that in the midst of all this chaos, all this craziness, that you help us, Lord, to find regularity in our days. That you help us to find joy in the little things like really long days with more sunlight. And Lord, help us not to get so pent up as we are sitting at home, Lord, in a lot of ways, just kind of on our own. I ask, Lord, that you be with us, that you bless this time. In Jesus' name I pray. Amen. All right, so here I have an example. I always want to throw a couple graphs at you guys. Reading graphs is an essential skill, not just for science class, literally for life. So I have a class that was studying speed and momentum of a 0.25 kilogram ball dropped from a bridge. Obviously, it's dropped from a bridge. You have two things working with it. You have the time here. This is a momentum versus time graph. You have time down here at the bottom. Every second that this ball is dropping, it is accelerating. Okay. Now that's important because that means that the speed is going up, which obviously, if you're calculating momentum, that means the momentum is going to go up because momentum is a calculation of kilograms times velocity. So if the velocity is increasing because the acceleration of gravity is 9.8 meters per second squared, which means that every second you're going to go 9.8 meters per second faster. So if the acceleration is increasing, or thus the velocity is increasing, and the kilogram mass is staying the same, then your momentum is going to go up with time, which is why we see this linear relationship. We know that in 2 seconds' time, it is accelerated to the point of having a momentum now of 5 kilogram meters per second. You could figure out the speed specifically to that by basically changing the formula around for momentum and trying to find speed. But just understand that obviously those two things are related. All right. Don't worry about that. So this was actually part of your assignment last night. I'm sorry. I thought that I'd gotten to this, but I guess I didn't. But it talks a little bit about the law of conservation of momentum. It says if no net force acts on a system. Now, that is a big assumption, okay? That whole big, if no net force acts on a system, it seems very unassuming and it seems very nonchalant, but it's a huge caveat, okay? Because here's the thing. Is there always forces acting on a system? Of course. Okay, friction, gravity, things like that are always going to come into play. Okay, there's no such thing as a frictionless machine. All right, there's no such thing as a place where there's no gravity. I mean, you can artificially, potentially create that, or even go up in space and create it. But here on Earth, that's never going to happen. So this is a really big statement. But if we can exclude all net forces, then the total momentum of the system does not change. In a closed system, the loss of momentum of one object equals the gain in momentum of another object. Momentum is always conserved. All right? Now, what does that actually mean? Think about billiards. Some of you guys are going, I don't know what billiards is, Mr. Ruddy. Yes, you do. Think about pool. That's another name. Billiards is just a fancy name for pool. All right, so if anybody, I don't know if anybody watching right now has a pool table at home, but if you have a pool table, the whole game is all about the law of conservation of momentum. What you are doing is you are delivering momentum to a ball using a cue. You're actually transferring the momentum, the force from the cue, or the pool stick rather, into the cue ball, and then that cue ball starts to move because of that transfer of momentum. The cue ball then hits another ball, another billiard ball, and it transfers its momentum to that other ball. If you guys are good at pool, you're probably able to hit a ball with a cue ball. The cue ball stops in its tracks 100%, and all the momentum is carried over to the other ball. Okay? Maybe you guys have seen those shots before. I don't have an example of it. I wish I did. Where, again, all the momentum is transferred, the other ball moves, the cue ball stops in its tracks, and momentum is reserved. One of the reasons that you have felt on that table, if you guys have ever felt a pool table, it's to lessen the impact of friction. Because, of course, this is not a closed system, and friction's always going to be at play. So if you let a ball roll on a pool table, eventually it'll slow down because of friction. But initially it doesn't, because the felt kind of helps it roll effectively. And again, a lot of that momentum is transferred from one ball to the next. All right. So here we have an example of train cars. Why are trains on tracks? Anybody know? Okay, we're talking about really massive things. Train cars are not small. They're not light. They're on tracks to reduce friction. That's the main reason. So here we have we're going to assume a nearly frictionless track. Okay, this car, before the collision, is moving 10 meters per second. It's going to come into contact really hard with this car at 0 meters per second. So its momentum right here is 3,000 kilogram meters per second. Its momentum right here is 0. As soon as they hit, this car stands still, it stops. The other car gains all the momentum on the other side. So we go from 3,000 kilogram meters per second to 0 kilogram meters per second. But where did the momentum go? It got transferred. None of it was lost. It got transferred to the car next to it, the green car. So now the green car is moving at 10 meters per second and has a momentum calculation of 300,000 kilogram meters per second. I may have said 3,000 earlier. Sorry. Now, is this scenario actual? No. Because again, even with putting really good bearings on these wheels, making them easily to rotate, even with putting them on tracks to try and limit the friction that's available there. Is there friction on a train? There's incredible amounts of friction. So this is never going to be a perfect split where you get 300,000 kilogram meters per second transferred directly to another 300,000 kilometers per second. this is going to experience loss. It's not going to move nearly as fast. We showed the Newton's cradle. It's the same concept. As one ball hits the other, the momentum is transferred to the other ball. But even with that, even with a near frictionless environment of a Newton's cradle, do the balls as they swing, do they eventually slow down? Yes, they do. All right, let's not worry about the quiz here. Okay, so I'm going to start with the fundamental forces. I'm going to let this video kind of explain it. I only ask for a couple of them, really more than anything. But this is the last section of this chapter. So we'll deal with kind of the consequences of that. We might have a couple more slides.
This episode was proudly
but I'm going to let you guys watch this
all-new
first.
2015 Subaru Legacy. It's not just a sedan, it's a Subaru.
I'm so attracted to you.
You mean because of one of the 4 fundamental forces of physics, namely gravity?
Yeah, gravity, that's it.
Hey guys, thanks for watching D-News. It's Trace and Julian here. Theoretical physics can get super complicated, as you probably know. M theories, grand unified theory, gravity waves, quantum, everything is crazy.
Now, the standard model of physics is a little easier to wrap our collective noggins around, but even still, there are knowledge gaps. For example, this week, physicists published in Physical Review Letters that they discovered a particle that might hold the universe together.
Oh, great. No big deal then. That's cool.
Yeah. But the particle, which has a name but I have no idea how to say it, is comprised of 2 quarks. Together, these tiny particles are 3 times heavier than a proton and might give hints as to how an atom's nucleus holds together.
We know the strong nuclear force holds the nucleus together, but how it works is a mystery, in spite of it being one of the 4 fundamental forces of physics.
Now, the 4 fundamental forces from strongest to weakest are the strong nuclear, the weak nuclear, electromagnetism, and gravity.
You already know what strong nuclear does. It holds atoms together, overcoming the repulsion of positively charged protons from each other. Weak nuclear is what causes the beta decay of atoms. Weak nuclear allows for the buildup of radioactive isotopes and thus the creation of something like deuterium that helps the sun burn.
Subatomic forces are very difficult to study because of the scale of the objects. So the announcement of the particle d whatever is a big deal for physicists.
Though admittedly, it doesn't really do much for you day to day.
Unlike the other 2 fundamental forces which are acting on you right now. The most obvious is gravity, which holds you to the planet, holds the planet to the sun to the galaxy together, and so on and so forth. But we'll come back to that in a minute.
Electromagnetic force is what causes static electricity to hold, say, a balloon on the wall after you rub it on your head.
Or the force that makes magnets attracted or repel each other.
Both gravity and electromagnetism are properties of matter. They're directly proportional to mass and electrical charge, respectively, and they both have infinite range. The gravity of the moon is acting on you right now.
Now, the mind blower is that of all of these, gravity is the weakest. Seriously, a balloon or a rocket can overcome gravity. The Earth is unfathomably gigantic in comparison to me, and I'm defying the entirety of its gravity right now. Though, not for long.
Physicists found a particle on the quantum level that aligns to each of these 4 fundamental forces, mostly. The strong nuclear uses pions and gluons. The weak nuclear uses W and Z bosons.
Electromagnetic force uses photons, yes, the same as light energy, because light is part of the electromagnetic spectrum. Gravity uses gravitons, which is tricksy.
Albert Einstein said gravity works because it curves the space-time continuum around all objects. The larger the object, the more gravity, but why is a mystery. Scientists have never found a graviton, though they have discovered gravity waves, maybe. The jury is still out.
Gravity is so confusing because we can't explain black holes with current gravity calculations, and it seems to break down at the atomic level, too.
In the end, the 4 fundamental forces of physics might sound decided and explored, fundamental forces, but scientists are still scratching heads a lot.
Now, do you want to know more on physics? Well, over here we have a video about gravity waves with Ian.
And also, you can comment down below and let us know if you have any science questions about whatever.
Yeah, we like that.
Okay, so This obviously goes into depths that I'm not willing to explore necessarily with you guys. Some of these we've talked about. We talked about earlier in the year, definitely the strong nuclear force. We talked about the attraction between protons and electrons, which is what keeps all the atoms within our body together and not exploding apart, which is kind of important. And of course, we've talked about gravity. We haven't talked about electromagnetism very much yet, and we definitely haven't talked about radioactive decay or the weak nuclear force that much either. We probably won't get to the weak nuclear force. I'd like to talk about electricity and the electromagnetic force. But again, these are the forces that keep our world together as we know it. So they're really important, and we're gonna talk about these four forces just briefly in this last section to kind of touch on it. I think I'm gonna stop here though. It's been about 15 minutes, so this is a shorter video than normal. Oh, I totally forgot though. The question for today is, what is my dog's name? His name is Louis. So the question for today is, what is my dog's name? His name is Louis. So you had to watch to the end to get to that. But again, we will cover the rest of this. I just kind of wanted to introduce it to you today. We'll cover it next time. I'll see you guys Monday, I guess, for part of the time. And we'll talk about kind of what we're going to do with that test and everything to finish this chapter up after we finish these notes. All right, guys, stay healthy, stay safe. Talk to you later. Bye.